All right, kinetic molecular theory of and gases. This really pertains to gases, but all states of matter have some type of movement to their particles. So, as a quick, fun, easy review, what are the three states of matter? Solids, liquids, and gases. Oh, plasma is the fourth state, but we don't really talk about it much. So looking at the diagrams, the little balls represent atoms or molecules. In a solid, those atoms and molecules are really tight and compacted together in a very orderly fashion. Liquids, we get a little bit more chaos to them. They're free-flowing. And then gases are the most spread out, have the most spread out molecules. They also have the most chaos and random motion to their particles. So, the kinetic molecular theory is a theory that explains the states of matter and is based on the idea that matter is composed of tiny particles that are always in motion. The term kinetic means moving. An ideal gas is an imaginary gas whose behavior perfectly fits all of the assumptions of the kinetic molecular theory. So on the next slide, we'll talk about the kinetic molecular theory, or the 5 assumptions of it. In reality, gases are not ideal. However, they are the closest state of matter to perfectly fulfilling this kinetic molecular theory. So, the 5 assumptions of the kinetic molecular theory are that gases consist of a large number of particles that are very far apart from one another. So, most gases have a lot of empty space incorporated into their volume. Gas particles are in constant rapid motion in random directions. Collisions between gas particles and between the particles and the walls of the container are elastic. That means that the particles or the gas particles will bounce off of one another if they hit another gas molecule, or they will bounce off the sides of the container. The 4th assumption is that there are no forces of attraction or repulsion between gas molecules. So that means we're not worrying about cations or anions. There's no positivity or negativity. And then the average kinetic energy of the gas particles is dependent upon the temperature of the gas. So as the temperature of the gas increases, so will the average kinetic energy. Or if it decreases, the average kinetic energy will go down. By definition, temperature is the average kinetic energy of anything. So when we talk about gases, we have to deal with pressure. Pressure is the force per unit area on a surface. That gives you the mathematical formula P equals F over A. Earth's atmosphere exerts pressure because of gravity acting on a huge number of gas particles. Gas pressure is then the pressure that results from the collision of gas particles with an object. So this diagram is showing you the random motion of the gas molecules and then how they bounce off the container and change, or the walls of the container, and then change directions. So when we measure pressure, we can look at the atmospheric pressure. This is the pressure exerted by the gas particles in Earth's atmosphere as those particles collide with objects. This is slightly dependent on the weather. There are 3 devices that we can use to measure pressure. A barometer is an instrument used to measure atmospheric pressure at sea level. Mercury will rise to 760 millimeters. We will talk about those numbers here a little bit on the next slide. At Mount Everest, so up in the mountains, the pressure is only 253 millimeters of mercury. So as you increase in elevation, you will decrease in pressure. I don't even know how to say that. An aneroid barometer looks at the contraction and expansion of springs. That would be right here. And then a manometer is the pressure of an enclosed gas, and it can measure the height as it changes due to pressure. I would say barometer is probably the one, or the term at least, you guys are most familiar with when they talk about barometric pressure.
Is that millimeter like a radar tester or something?
I don't believe so. All right, so there are units of gas pressure, millimeters of mercury, torrs, pascals, and atmospheres. So there are 4 different units, and they can all be converted among themselves with these conversions. So 1 atmosphere equals 760 millimeters of mercury, which equals 760 torr, which equals 101.3 kilopascals. So these conversions will help you convert between the 2 or 3 or whatever is being asked of you. Pascal is the standard unit for pressure. Often it'll be in kilopascals though, just because you're dealing with a much larger number. So to practice converting between these measurements, the atmospheric pressure in a mountainous range location is measured to be 613 millimeters of mercury. What is the pressure in atmosphere in kilopascals? So this would have to be 2 separate railroad tracks to solve these. Always start with what you're given. 613 millimeters of mercury. And so millimeters of mercury goes on the bottom. And we're converting it into atmospheres. So looking back on this previous slide, what is the relationship between an atmosphere and millimeters of mercury? One atmosphere, good. So 1 atmosphere to how many millimeters of mercury?
760.
Good, 760. So multiply across and then divide. And what did we get? 807 or 81. Good. Any questions on how we arrived at that? Okay, so then converting this 613 into kilopascals, what would be your relationship for this conversion?
760 milliliters or whatever.
Yep, 760 millimeters of mercury.
And then 101.3 kilopascals.
Yep. And when you run the math, you'll get 81.7 kilopascals. Any questions on how to convert between the different units of pressure? Okay. All right, so kinetic energy and heat. When a substance is heated, some of the absorbed energy is stored, while some of the energy increases the speeds at which the particles are moving. So, average kinetic energy at any given temperature, not all of the particles in the sample will have the same kinetic energy. That means some are moving faster and some are moving slower. That's why we look at the average. At a given temperature, the particles of any substance will then have the same kinetic energy, same average kinetic energy, because that's how averages work, I guess. And so the colder the sample, if you have more molecules, it'll have fewer energy or less energy for the same number, or for fewer particles but a higher temperature. So basically, if it's hotter, it's going to have a higher average kinetic energy, and vice versa. Absolute zero then, what temperature is absolute zero? 0 Kelvin, good. This is a temperature at which the motion of these particles will theoretically stop. However, this has not ever been reached either in the lab or naturally. So that's why they call it theoretical, because they don't actually they haven't actually achieved it, and they don't actually know what happens. They have an idea, they've theorized about it, but they don't actually know what happens.